hydrogen bonds in amines. So hydrogen bonds are stronger in primary amines than in secondary amines. The dipole-dipole interactions are stronger in primary amines, so the difference between a nitrogen and a hydrogen bond is a stronger dipole than the difference between a carbon and nitrogen bond. And of course, in a primary amine, there are more NH bonds. Another way to explain the stronger hydrogen forces in primary amines is to count how many hydrogen bonds primary, secondary, and tertiary amines can make. And we can do that by counting the number of covalent bonds to hydrogen and the number of lone pairs. So a primary amine has 2 covalent bonds to hydrogen and 1 lone pair on the nitrogen. So it can make 3 hydrogen bonds. My pen. How many times do I have to tell you? Okay, so 3 hydrogen bonds. 3 hydrogen bonds for a primary amine. Because of 2 covalent bonds to hydrogen and 1 lone pair. A secondary amine has only 1 covalent bond to hydrogen and 1 lone pair, so it can only make 2 hydrogen bonds per molecule. And a tertiary amine interacting with another tertiary amine does not have any NH group, and therefore it can make 0 hydrogen bonds. So what we should say is that a tertiary amine can only make hydrogen bonds if in solution with a molecule that has an OH, NH, or HF group. So alcohols, a tertiary amine can make a hydrogen bond with an alcohol such as ethanol. A tertiary amine could make a hydrogen bond with a primary amine such as methylamine. But a tertiary amine cannot make a hydrogen bond with a tertiary amine because there is no hydrogen or NH group which is required for a hydrogen bond to form. The structure of proteins is largely dependent on the formation of hydrogen bonds. Alpha helixes and beta sheets are often thought to be held together primarily by the hydrogen bonding in the backbone. So the structures alpha helix and beta sheets are structures are held in that specific shape through the hydrogen bonding interactions of the amino acids. And there are also hydrogen bonds between DNA base pairs. Hydrogen bonds hold our 2 strands of DNA together. The daughter DNA and the template DNA are held together by hydrogen bonds. They are not covalently bonded, so the duplex only exists because of hydrogen bonds. And one of the things that you will need to know in biochem is that AT pairs make 2 hydrogen bonds and GC pairs make 3 hydrogen bonds. Why is this significant? Why are the types of functional groups significant, the physiological properties, and the polarity and dipole moments, and etc.? Well, compounds that have similar shapes and properties will have similar physiological activities. So we can compare the naturally occurring salicylic acid, which is in willow bark, and people used to chew willow bark as a pain reliever. Can act as a pain reliever. However, it has really intense side effects of upsetting your stomach. Aspirin, and this molecule has a carboxylic acid here. Aspirin, which we know is a pain reliever that was derived from willow bark, salicylic acid, contains a carboxylic acid and is an analgesic. Ibufenac, which is a NSAID, a prescription NSAID, also has a carboxylic acid group, as does ibuprofen, another NSAID, and naproxen. All of these have this carboxylic acid group, and it's relatively the same, it's near the same position, having this benzene ring. They all have the benzene ring, and so they have similar properties. The only one that doesn't have a carboxylic acid has an amide group, but the amide group is structurally similar to the carboxylic acid. We simply have replaced an OH with an NH. And these molecules have similar properties in terms of London dispersion forces, dipole-dipole interactions, and hydrogen bonding. Okay. More physiological properties of molecules. One of the things that we have to consider when we are looking at melting points of a crystal is how tightly the crystal packs together. So we have a rule that alkanes with an odd number of carbons pack less tightly than alkanes with an even number of carbons. And this has to do with that if we have an odd number of carbons, then we never have overlap. But if we have an even number of carbons, then one row of the molecule can overlap with a second row of the molecule, which results in a closer packing. We can also know that if packing affects melting point, then a branched molecule, such as the one drawn in this circle, will have less tight packing due to the inability of molecules to get super close to each other when they have extremely high branching. And a physiological example of this is for the cell membrane. In the cell membrane, a high number of the phospholipids have what we call kinks in the chain, or cis double bonds. Cis double bonds pack less tightly than trans double bonds. So a cis double bond versus a trans double bond, right? So a trans double bond is a zigzag. Zigzags pack more tightly. And a cis double bond is not a zigzag. It has a kink. So it sort of bends in on itself. And that means that it packs less tightly and is more liquid. So that allows the cell membrane, when it has many cis bonds and the phospholipid tails, to be more fluid, because trans bond results in solid oils. Cis bonds result in liquid oils because they have a lower melting point. And we want our cell membranes to be less solid and more fluid. Solubility of molecules. Remember the rule from Gen Chem that like dissolves like. Polar compounds dissolve in polar solvents, and nonpolar compounds dissolve in nonpolar solvents. And as the ratio of carbon to oxygen decreases, so as we increase the amount of carbon relative to the amount of polar atoms like oxygen, the solubility of the molecule in a polar solvent decreases. And we have a rule that one oxygen can drag 3 carbons into polar solvent. Ooh. So when we get to having more than a 3-to-1 ratio of oxygen to carbon, then we are less soluble in a polar solvent. So ethanol is soluble in polar solvent, and propanol is soluble in a polar solvent, but butanol and pentanol and hexanol, as we increase number of carbons, then the solubility is decreasing, because as you increase the number of carbons and you maintain only one OH group, you are increasing the amount of dispersion forces, but you are not increasing the amount of polar forces. And so the amount of the dispersion or hydrophobic force is getting greater. So we need to talk also about solvation. So solvation is the interaction of water, specifically water molecule, with a molecule that has a dipole. And because of this interaction, it causes the substance to dissolve in water. So we've already talked about this in Gen Chem with salts like sodium and chloride, where the salt completely dissociates and sodium goes into solution and chlorine goes into solution. For organic molecules, it's not quite the same, but it's still dissolved in solution because the molecule is surrounded by water and it no longer appears solid. So, and it is again the alignment of dipoles. So for the alignment of a negative dipole in water to a positive end of a dipole of another molecule. So that the molecule is surrounded by water molecules. That would be called solvation. And oxygen can drag 3 carbons into water. And so we have a chart showing this. I've already said this on the previous slide, but we have that 2 carbons. So this dimethyl ether is soluble. The methyl ethyl ether is soluble, but when we get up to 4 carbons, we're only slightly soluble. We go to 5 carbons, minimally soluble, and 6 carbons is insoluble. So as the number of carbons increases relative to the same number of oxygens, the solubility decreases. And you should be able to rank molecules like this in terms of their solubility. Continuing, like dissolves like is an important drug interaction. So the blood-brain barrier has a fat-soluble barrier. That means it's hydrophobic. So in order to penetrate the blood-brain barrier, our molecule must be capable of passing a hydrophobic barrier. Things that can pass hydrophobic barrier tend to have, we need solubility, which means, and since our bloodstream is very polar, it needs to have a polar portion of the molecule to be soluble, but to pass the blood-brain barrier, it needs to have a hydrophobic portion of the molecule. And so drugs that pass the blood-brain barrier tend to be amphipathic in nature, like a phospholipid. They have to have a polar part for dissolving and a non-polar part for crossing the blood-brain barrier. And so here are some examples of things that can cross the blood-brain barrier. THC and pentothal have hydrocarbon tails that facilitate crossing of the barrier. So we have a portion that is soluble in aqueous solution and a portion that is not soluble in aqueous solution. Solubilities of alkyl halides. As the number of carbons increases relative to a constant number of halogens, the solubility decreases. So as you increase the hydrophobic character of the molecule, which are carbons and hydrogens, or the oily part, the solubility decreases. If we were to increase the number of halogens and leave the number of carbons constant, then the solubility would increase. And that's how that would work. So we have polar versus non-polar. Carbons are considered carbon hydrogen groups are non-polar, and the halogens are polar. So we have both characteristics in the molecule. If you increase the polar part, it becomes more soluble. If you increase the non-polar part, it becomes less soluble. Cell membranes, these are amphipathic. You should have studied cell membranes in Bio 1. We have phospholipid molecules, polar head, hydrophobic tail. These are amphipathic. That's an amphipathic. The definition of amphipathic is having a polar portion and a hydrophobic portion. And the polar portion is interacts with the aqueous or polar solvents, and the hydrophobic portion interacts only with hydrophobic solvents or non-polar solvents.